Let's continue with some of the art of problem solving example questions. So this is problem 1.2.2 in AoPS. So this one asks us, prove that for any a less than or equal to b, so these are going to be real numbers now, a and b are real numbers and a is less than or equal to b, the open interval a to b is indeed an interval. Okay, so before even identifying the assumptions and conclusion, you might say, well, of course, an open interval is an interval because it has the word interval in it. But of course, that argument doesn't make any sense because we've defined the phrase open interval, so this has one definition, and then we had a different definition, which they highlight for you in the parenthetical here. We had, maybe I should call this definition 1, and then we had a second definition of the word interval, which I'll call definition 2, and I'll show you in a moment. So just because the word interval happens to appear in both of those definitions, that doesn't mean that they're actually the same. I mean, likewise, if you were programming and you defined one variable called, I don't know, myVar, and a second variable called var, you wouldn't say, well, of course, the two numbers, or the two variables, have to be equal. So you wouldn't say var is necessarily equal to myVar just because the same word variable, or var, appears in both of them. No, of course not. I mean, this is one thing. You could assign this the value, say 1, and you could assign this the value 2, and then they wouldn't necessarily be equal. They're just different names. So we have to be very careful. We treat open interval, that phrase, as a single atomic thing, which we defined, and then we treat this word interval as a separate thing, which we defined, and now we have to check that an open interval satisfies that definition of interval. Okay, so let me go to the book quickly and remind us of what those definitions are. So here's from the first reading on page 10. We say a subset I of the reals is called an interval if for any two numbers a and b in I, and a real x such that a is less than or equal to x is less than or equal to b, we have that x is in I. So this just means something is an interval if basically whenever two numbers are in the interval, everything between them, a between x and b, is still in the interval. This is a betweenness definition. But then we had a separate definition down here. The open interval AB is defined as this set of all numbers, a less than or equal to x less than, not equal, a less than x less than b. So let's write those two definitions. So I is an interval. This is the definition of interval if whenever a, b are in I, and a is between, x is between a and b, it's necessarily true. That's what this arrow means. It's necessarily true. Maybe I shouldn't use that notation. Then it's true that x is in the interval. Okay, so that's our definition of interval. Let me just separate this a little bit. And then our definition of open interval. So open interval is defined by two endpoints, a, b, and that was the set of all reals, if I have enough room, such that a is less than x is less than b. Okay, so it's a bit tight on space here, but okay. So those were our two definitions. We had a definition of interval and a definition of open interval. So now maybe we can identify the assumptions and conclusion, although I'm running out of space, so I'll do it down here. The theorem is not phrased in a way that makes the assumptions and conclusion very clear, so we have to kind of figure it out. The assumptions are, well, if let's let I equals a comma b. So I'm just going to give the interval a name. A, well, these are both real numbers, so I should tell you what they are. A, b, and r. And a is less than or equal to b. The conclusion is that this set I satisfies the definition of interval given above. Satisfies this definition of interval. Okay, so this goes to show that I think just parsing the statement of a proof and understanding precisely what's being said can often take some effort. Okay, so now I think we understand what we're trying to show, right? Our assumption is that I is this open interval using this definition, which I've written here in green. What we need to prove is that that set satisfies the first definition, which I've written in pink up here, which is that for any pair of numbers in the interval and any x between those numbers, that number x also belongs to the interval. It satisfies this betweenness property. Okay, so let's read the proof. We must show that if c and d are in the interval ab, this is what I've been calling I for shorthand, so I mean, that variable isn't used in the proof, but just to compare to what I've written down here. So if c and d belong to the interval, and x is between c and d, then x is in a and b. Okay, so what is this sentence doing? The sentence is just reminding us of the definition of interval, and it's really a guidance sentence, since it's telling us we need to prove this in order to show that it's an interval. So this is guidance text explaining what we're going to do, and it's reminding us of the definition of interval. Okay. What next? It says, but we know that a is less than c, and that d is less than b. How do we know that? Well, if c and d belong to the interval a and b, this is from the definition of open interval that every pair of numbers in that interval lie between a and b. So if c and d are both in the interval, they satisfy the definition. So this is a deduction from the definition, which I call definition 1 of open interval, right? So we use the definition of open interval to conclude that those two numbers in the interval satisfy this definition here. Okay, then it says, so we have, so this is going to be another deduction, a less than c, which follows from what we said a moment ago. C is less than or equal to x. Okay, well that's from this assumption up here. X is less than or equal to d. That is from this assumption up here. And d is less than b, and that's what we got a moment ago from the definition. So this is kind of combining inequalities. Combine inequalities. So this is a deduction, but I think it's pretty clear why it's true, since we've just combined a chain of inequalities. And then we say, so in particular, a is less than x is less than b. Okay, so that's just kind of from the previous line. I think it follows pretty clearly that if we just look at a, x, and b, that this is from the previous line. It's a deduction which is pretty clear to see. And then the final deduction is that x belongs to the set AB, and that's again from the definition. Maybe I should use a different color, because remember we had this definition that the open interval is all of the numbers satisfying this property. We've just shown that x satisfies that property, so that means this is a deduction, bad circle, this is a deduction from definition of open interval again. So this is again from definition 1, which I've written above. Okay, so what was the punchline? We had two definitions, a definition of interval that required this betweenness, a definition of open interval, which was given explicitly by this set, and we were trying to show that the open interval satisfies the other definition of interval. So again, resist the temptation to kind of let your eyes roll back and gloss over this example, because it seems maybe superficially obvious, and as you read it, maybe all of the statements sound obvious, but the litmus test for whether you're understanding a proof is not whether it sounds intuitive or you believe that it's true, it's whether you can explain why every deduction follows, and you can point precisely to a definition and say, this is where this definition is being used, this is why this deduction is true, this is how we showed the conclusion must hold. It's not just about believing it, it's about understanding the chain of logical reasoning. Okay, that's all for today.